Hi, this is Mrs. Doris. This is Lesson 6-1 entitled Solving Systems by Graphing. The objective is that you will be able to solve systems of equations by graphing and that you will be able to analyze special systems. Special systems are ones that have no solution or they have an infinite number of solutions. The reason systems are so important is because we can use them to solve real-life problems. And when we return in January, we will be solving a number of real-life type problems. Vocabulary, we're starting with two definitions. First of all, a system of linear equations is simply two or more equations taken together. Then, a solution of a system of linear equations is any ordered pair that makes all of the equations in the system true. Okay, problem 1. Solving a system of equations by graphing. What is the solution of the system? Use a graph and check your answer. All right, I'm going to begin with the first equation, and I'm going to do it in blue. I am going to use the slope-intercept form since these are already written in that y equals mx plus b form. If you prefer doing a table, then you might do a table and make sure that your graph looks exactly like ours. However, I would encourage you to follow along and maybe listen to it even twice in order to grasp how you graph using this form. All right, well, the number that's added on, in this case a positive 4, is where we start on the graph. Positive 4 is our y-intercept, so I'm going to put a point there. Our slope is the coefficient of the x term, which is 2, or 2 over 1. That means that we rise 2 and run 1, and we could also go down 2 and left 1. All right, so down 2 and left 1, and I'm going to continue this. This will be very important in this lesson because we don't know where the two lines will intersect, and that's what we're looking for. All right, so I'm going to draw a line as straight as I can. And you may wish to use rulers on this because we are going to be looking for a point of intersection. Okay, the second equation I'm going to put in red. And here we start at a y-intercept of positive 2, which would be right there. Our slope, the coefficient of x, is an invisible 1. 1 can be written 1 over 1. It can also be written as negative 1 over negative 1. Negative divided by negative is positive. So I can go rise 1 and run right 1 and keep doing that. And I could also go down 1 and left 1. There's our point of intersection. And again, continue doing it so that we have a nice long line. All right, so it appears that our point of intersection is right at negative 2, 0. All right, so let's use that point and check it in each of the equations algebraically. All right, so taking my first equation again, y equals 2x plus 4, I'm going to put the 0 in for the y, and for the x, I'm going to put in negative 2. And we're going to see if this works. All right, so 2 times negative 2 is negative 4. And negative 4 plus 4 is equal to 0. So yes, negative 2, 0. checks out in the first equation. Okay, then we're going to take our second equation and see if negative 2, 0 works for it. So again, 0 is the y. My x is negative 2. And I want to add 2, and yes, negative 2 plus 2 is 0. So since it works in both equations, our solution is negative 2, 0. All right, problem 2, writing a system of equations. One satellite radio service charges $10 per month plus an activation fee of $20. A second service charges $11 per month plus an activation fee of $15. In what month was the cost of the service the same? All right, so the first thing that we have to do in a word problem is identify our two variables and define them. So you'll see in the last sentence, which is a question, what the two variables would be. It asks in what month, so let's use M for the number of months, was the cost of the service the same? And so the second one is cost, and I'm going to use C for the cost. Now, in looking at these, which one would be our independent variable and which one would be our dependent variable? Well, time is most always independent, and in this case, that would be our number of months, which is the x. The cost, which would be like our y, is dependent upon how many months. All right, so I'm going to go ahead on our graph and label the axes. Months will go across the horizontal axis, and cost will go on the vertical axis. All right, now let's write our equations. We are told, going back to the first sentence, one satellite radio service charges $10 per month. All right, so all of our equations are going to start with the cost, which is our y. Cost is equal to $10 per month would be 10M plus an activation fee of $20, so plus 20. And there's our first equation. Our second equation is for the second service, which charges 11 per month. So we would write C equals 11M, and then plus an activation fee of 15. All right, so let's decide how we're going to label our axes. And I think perhaps on months, each square will represent 1 month. So I'm going to label every other, okay, and that may be far enough, we'll see. And then on cost, we need to start at 15 and 20, and it's going up by 10. So I think I'm going to let every square represent $5. So I'll label this 10, 20, 30, 40, 50, 60, and 70. All right, hopefully that will be far enough. All right, so I'm going to graph my first equation, C equals 10M plus 20. Now this one is going to be fairly easy to do because we have a y-intercept of 20, which will go right here, which makes sense because when M is 0, 10 times 0 is 0, and 0 plus 20 is $20 for the cost. Our slope is 10 or 10 over 1. So up 10 and over 1. Up 10 and over 1. And of course you have to be careful. We're not counting up 10 squares. We want to go up $10. So this would appears to be the graph of the first equation. All right, now let's take a look at the next one. Now the next one poses a little bit of an issue because our slope is 11. But let's go ahead and see what we can do. We have a y-intercept of 15, which would be right here. Then we're going up $11 a month, and this can be a little bit harder to graph, particularly when we're using big numbers, or they're not huge, but bigger than single numbers. So let's see what we can do. All right, up 11 would be to 26 and over 1. Up 11 would be up to 37 and over 1. Up 11 and over 1. Up, let's see, 11 and over 1. Up 11 and over 1. And I probably need to get my dots a little bit better. Let's see. 15 and 11 is 26, and 11 is 37. That should probably be up a little bit higher. And 7 is 48, so a little higher. And 11 is 59, so it should be almost right here. And then another 11 would put it right here. All right, so unfortunately on our graph, these lines are almost on top of each other, but not quite. All right, it does appear, however, and by the way, this kind of points out one of the problems with graphing, and that is it can sometimes be difficult to tell an exact solution. We can see that the graphs are going to cross, but at what point can be unclear. And so that is one of the problems with graphing, and particularly when you get a solution that is not a nice whole number in your ordered pair. So, but let's try this. It appears that we have a solution at 5 months and $70. So let's check it out. And I'm actually going to do it over here on top of the graph just because I'm running out of room. So taking this equation, it appears the cost is $70, and I'm going to take 10 times the number of the months, which is 5, plus the activation fee of 20. And it's looking good so far. 10 times 5 is 50. 50 plus 20 is 70. So it checks out in the first one. In the second equation, let's substitute 70 in for the cost. This time we'll take 11 times 5, and we're going to add 15. All right, 11 times 5 is 55, plus 15, and once again, we do get 70. So it checks out in the second equation. So the question, in what month was the cost of the service the same? And we would say in the 5th month, the cost is $70 for both services. All right. If you have any questions, of course, please jot it down at the bottom of your notes and then ask on Friday. Okay, a few more vocabulary words. And this has to do with our graphs. First of all, the word consistent is a system of equations that has at least one solution. An independent system is one that is consistent, that has exactly one solution. So the one that we just did had one solution. It would be considered consistent and independent. A dependent system is a consistent system that has infinitely many solutions, and an inconsistent system is one that does not have any solution. All right, so let's look at problem 3. Systems with infinitely many solutions or no solution. Now, on your notes, you may note that I did not give you a graph for these. So I'm going to give away the answer and tell you where to plot these under the concept summary. And you may just want to draw an arrow over to the graph in question. So here we are. A is going to be a no solution. So draw an arrow over to the no solution and we'll go ahead and graph. All right, I'm going to do this first one in blue. We have a y-intercept of -3 and we have a slope, part of it's invisible, of -1. That could be -1 over +1, or we could write it as +1 over -1. So we'll use both. Let's do this one first. That would be down 1 and right 1. Down 1 and right 1. All right. And now let's use this slope. That would be a rise of +1, but left 1. Rise 1, left 1. And we'll continue to do that until we reach the limits of our graph. Okay. So drawing my line. There we go. Okay, let's do the second one. And this time we're going to use red. My y-intercept is +5. And my slope, again, is -1. And you may already notice that the slopes are the same. So when that happens, we have parallel lines. Let's go ahead and use the slope to graph. And you can see they are indeed parallel. All right, these two lines are never going to intersect. They remain the same distance apart. So our answer to this would be no solution. And you can simply write out the words, or if you prefer a shortcut, you can write the empty set. Now please note that is not a symbol for 0. 0 is an answer. So the empty set does have, it looks like a 0 with a line slashed through it. All right, let's go to B. And the equations in B, you can draw an arrow to the middle graph, infinitely many solutions. All right, so here we go. Let's graph this one. And I'm going to use blue for the top equation. Y-intercept of -3. And we have a slope of 3, which can be written 3 over 1. So let's go up 3 and over 1. Rise 3, run 1. Rise 3, run 1. And I can also go down 3 and left 1 as well. And we'll draw our line as best we can. Try to hit the points. Okay? Now, the second equation I'm going to do in red, but before we look at that, it's not quite in slope-intercept form. But I can see I can very easily get it there by dividing all terms by 3. And remember, you have to divide everything by 3. 3y divided by 3 is y. 9x divided by 3 is 3x. Minus 9 divided by 3 is 3. So I'm going to graph this line in red. And you'll notice it's exactly the same now. I have a y-intercept of -3, which is right here, and a slope of 3, or 3/1, which is just right. I'm going to kind of draw it to the side so that you can see it's just right on top of this blue line. All right, so hopefully you can see that this is the same line, and so our answer to this is we have an infinite number of solutions. Or you can say infinitely many solutions. All right, now let's go to our concept summary. And on our concept summary, we're going to use problem number 1 for the first graph. So that problem was y equals 2x plus 4. So copy the graphs from problem 1 onto this. Okay, and the other equation was y equals x plus 2. All right, so this is where we had a solution right here at -2, 0. All right, so when you have one solution, you find that the lines intersect in one point. The lines have different slopes. If I write my equations up here, y equals 2x plus 4, and the other one was y equals x plus 2. Note that's actually 1x, so our slopes here, 2 on one and 1 on the other, are different. The equations are consistent because we have a solution, and they're independent because we have exactly one solution. All right. Okay, on our middle graph with infinitely many solutions, hang on a minute, I put the wrong graphs. I'm going to pause this and redo it just a minute. Okay, my apologies. Got the wrong one in the wrong spot. But you should have yours graphed in this middle graph. All right, so here the lines are the same. The lines have the same slope and y-intercept. As you recall, we had y equals 3x minus 3, and both equations turned out to be the same when we solved the 3y equals 9x minus 9 for y. The equations are considered consistent and dependent because there is an infinite number of solutions. It is exactly the same line. All right, and then our last one, I'm going to pause it while I put the graph on here that you should already have. All right, this was y equals negative x minus 3 and y equals negative x plus 5. I'll label it 3a, and you may prefer to do that too. All right, so these lines are parallel. The lines have exactly the same slope, which was -1, and different y-intercepts. One has a y-intercept, the blue line, of -3. The red line has a y-intercept of 5. These equations are inconsistent. And that's what we call a system that has no solution. All right, this concludes our lesson today. If you have any questions, please jot them down, and I will see you in class. Thank you.